time, I'd like to start the sixth PMIP Wings seminar. We have, as usual, two speakers. Each speaker talks 20 minutes, followed by 10-minute discussion, and finish in 1 hour. To save time, I briefly introduce only briefly introduce speakers. The first speaker is Masanobu Yamamoto from Hokkaido University. He's going to talk about CO2 reconstruction based on Indian C3, C4 vegetation changes over the past 1.46 million years. So please, Yamamoto-san.
Yeah. So can you see the slide?
Yes.
Yeah. Thank you, Yoshimori-san, for your introduction. So good afternoon and good morning. I am Masanobu Yamamoto of Hokkaido University. Wait a moment. Okay. Then, this study was conducted by collaboration with Steve Clemens and there's a pointer. Okay. And Yonson Huan of Brown University, and Osamu Seki is my colleague, and Yuko Tsuchiya, my student, and Ryota Oishi and Ayako Abe of the University of Tokyo. So we reconstructed CO2 concentration based on leaf wax carbon isotopes in sediments from the Bay of Bengal. So as you know, that the reconstruction of CO2 concentration is essential to understand the history of Earth's climate. So ice core is a precious archive of CO2 concentration. This spans the last 0.8 million years. You see this zigzag blue lines, zigzag pattern is a beautiful ice core CO2 records. And before the 0.8 million years ago, we have to use the different proxies and the different archives. For instance, foraminiferous boron isotopes and alkanon carbon isotopes. So green one and red one, scattered here. So you will see the precision looks not good. And also resolution is generally not good, except for some specific interval. And blue one indicates the blue ice, Antarctic blue ice data. And this is the CO2 concentration in ice. So the concentration itself is precise, but the record is not continuous. So we really need the high resolution continuous record before 800,000 years ago. We analyzed the leaf wax carbon isotopes. We analyzed the long chain normal fatty acids, and the data is a black one, you see. This is the delta C13 value of the long chain normal fatty acid. So this was extracted from the sediment at the site U4046 IODP site in northern Bay of Bengal. So we actually intended to reconstruct the Indian summer monsoon precipitation by analyzing the carbon isotopes, because the carbon isotopes should reflect the C3, C4 vegetation, and the C3, C4 vegetation is believed to reflect the precipitation. But surprisingly, this pattern, is not consistent with the other precipitation proxy records obtained by other proxies. But the variation was very, very similar to the Antarctic ice core CO2 record, blue one. This is the EPICA CO2 record. So this was a big surprise for us. And we made the plot between the leaf wax carbon isotopes and epica CO2 concentration. So you will see a very good correlation between the two parameters. So this good correlation was obtained, for this interval during the last 800,000 years. If this relationship was true before the 800,000 years ago, we can estimate the past CO2 concentration based on leaf wax carbon isotopes. So this is a principle of my today's presentation. But why the carbon isotopes reflect the CO2 concentration? So this was a big question for us. So this is the long chain normal fatty acid. So this is the leaf wax of the terrestrial higher plants. And there are C3 and C4 plants in higher plants, and they have a quite different carbon isotopic composition. So if we see the carbon isotopic composition in leaf wax, then we can distinguish C3 and C4 plants, and also evaluate the relative abundance of C3, C4 plants. So the sediments were delivered from the East India, Mahanadi Basin, and the small coastal basin. So the carbon isotopes should reflect the C3, C4 vegetation in these river basins. So C3 plants fix carbon from CO2 in mesophyll cell by photosynthesis using enzyme Rubisco. But this Rubisco at the same time fixes the oxygen in the mesophyll cell and then loses the carbon. So this is called photorespiration. So in low CO2 condition, photosynthesis is suppressed compared to the photorespiration. So C3 plants cannot survive. So on the other hand, C4 plants converts CO2 to C4 diacid in the mesophyll cell. Then this diacid is transferred to bundled sheath cell. Then the CO2 is regenerated, and then this CO2 is fixed by photosynthesis using Rubisco. On the other hand, oxygen is not transferred to bundled sheath cell. So even in low CO2 condition, C4 plants can continue to photosynthesize. So this is the hypothesis of why C3 plants have advantage in high CO2 condition, and C4 plants have advantage in low CO2 condition. So this hypothesis was proved by experiment, free air CO2 experiment, enrichment experiments. So meta-analysis indicates that the production of C3 plants is more enhanced and in high CO2 condition. So in this study, Oishi-san and Abe-san used the vegetation model, and they examined the relationship between C3, C4 vegetation in East India at different CO2 level. This is the pre-industrial level, and this is LGM level. So the C3 vegetation coverage slightly decreased when CO2 dropped to the LGM level. On the other hand, the C4 vegetation substantially increased when CO2 dropped. So C4 vegetation increased in low CO2 condition. But there are potential factors affecting C3, C4 vegetation, temperature and precipitation and the CO2. So we Then Oishi-san and Abe-san examined the relationship, of the climate parameters and the CO2 level. So this indicates the world distribution of vegetation. C3 vegetation, the green, and the red indicates C4 vegetation. This is the pre-industrial and the LGM condition. So the study site, the climate of the study site indicated this black crosses. So precipitation and the temperature didn't change, between the pre-industrial and the LGM periods. But the red circles, C4 vegetation significantly increased in LGM CO2 condition. So this means that the East India is sensitive to changes in CO2 concentration, and the precipitation and the temperature changes were smaller and didn't affect the C3, C4 vegetation so much. And this is the result of the sensitivity test of the CO2. So with decreasing CO2, C4 vegetation coverage increased. On the other hand, the precipitation didn't affect so much the C4 vegetation coverage. And this map indicates the green colored areas where C3, C4 vegetation is sensitive to respond to primarily to CO2 change. It means whitish parts respond to temperature or precipitation. So our study site is located here. It's surrounded by the the area sensitive to CO2 change. So these regions are characterized by hot and seasonally dry climate. We call savanna climate. And also this map indicates that our application is applicable in other places, for instance, Africa and South America, etc. We also examined the relationship with temperature and precipitation proxy records at the study site. So this blue line indicates that Tex86 based sea surface temperature. This zigzag pattern is the glacial interglacial temperature change. And of course, in the interglacial, sea surface temperature was higher. Then during this period, C3 plants were more abundant. So theoretically and physiologically, C4 plants is expected to be more abundant in warmer and hotter climates. But the result is opposite to theoretical thought. So this suggests that the temperature was not a major factor affecting the C3, C4 vegetation. Then the green line indicates the oxygen isotopic composition of seawater of the Bay of Bengal. This was calculated from the planktic foraminifera oxygen isotopes by collection of temperature and the global ice volume. But this doesn't show a good correlation with CO2, C3, C4 vegetation, you see. And also the carbon isotopes, C3, C4 vegetation changes preceded the seawater oxygen isotopes. So this also indicates that the precipitation was not a major factor controlling the C3, C4 vegetation at the study site. So instead, we think that you see a very good correlation between the CO2 and the reflux carbon isotopes. So this strongly indicates that the reflux carbon isotopes reflected the atmospheric CO2. So there are two calibration lines, A and B. This is a linear and this is a curve. And the correlation determination is almost the same. So we tentatively use the linear calibration to estimate the past carbon dioxide concentration. So according to this calibration, the upper limit is the 3.25 parts per million, and the lower limit is the 151 parts per million. So this proxy works within the CO2 level between 151 to 325 parts per million. The calibration error is 12 parts per million. The calibration is site-specific and not to be applicable to other sites. And this method is applicable if precipitation and the temperature stayed in a particular range. The record is independent of ice core CO2 record. The obtained CO2 concentration is called the CO2 FA in this study and in our paper. So let's see the results of the CO2 reconstruction. The black one is the reconstructed CO2 concentration. Green one is the Antarctic ice core, and the yellow one is the blue ice CO2 concentration. So when we compare the blue ice and our records, there are large overlaps, but we have to see that the blue ice concentration is a bit higher than our reconstruction. So the discrepancy, between the blue ice and our reconstruction is still a question. It's not clear yet. So next we will see the comparison with LR04 delta 018. So this is the stacked record of the basic oxygen isotopic composition. So this is a proxy of continental ice volume and bottom water temperature. So you will see a good agreement between the CO2 and oxygen isotopes on orbital time scale. So cyclicity changed from the 41,000 year cycle to 100,000 year cycles across the mid-Pleistocene transition. So this covariation suggests that the CO2 and continental ice was tightly coupled on orbital time scales. But if we see the long-term mean trend, so this long-term mean trend is somehow different before the MPT. And oxygen isotopes gradually shifted in a positive direction until 700,000 years ago. But this trend was not seen in CO2 concentration. And also this mismatch indicates that the smaller continental ice coexisted in the condition of low CO2 before the MPT. So in contrast to oxygen isotopes, CO2 show a very good agreement to the carbon isotopes of basic foraminifera in deep ocean. So the carbon isotopes of the basic foraminifera should reflect the ocean circulation and the carbon storage in the deep ocean. So this good agreement, on long-term trend indicates that the long-term trend of the CO2 was regulated by the changes in the ocean circulation. So spectral analysis indicates the significant eccentricity and obliquity cycle after the MPT. And before the MPT, obliquity and probably double obliquity, it's about 80,000 year cycles appeared. And coherence was quite high at all orbital cycles. And the phase analysis indicates that there was a phase shift across the MPT. So before the MPT, CO2 variation preceded the variation of the oxygen isotopes. But after the MPT, the relationship was opposite. So this suggests that the interaction between CO2 and the continental ice was changed and reorganized across the MPT. We speculate that the changes in the deep ocean circulation might reorganize the interaction between the CO2 and the continental ice. Yeah, this is the summary slide. So there is a unique relationship between the CO2 and the reflux carbon isotopes. Then we used this relationship to estimate the past CO2 concentration. Then we found that the CO2 variation was tightly coupled with global ice volume and deep ocean circulation on glacial interglacial time scale. And the secular trend of CO2 was different from that of global ice volume, but similar to deep ocean carbon isotopes. So a shift in the relative phase of CO2 and ice volume cycles occurred during the MPT. So these findings suggest that deep ocean circulation controlled the long-term CO2 trend, and the interaction between CO2 and the continental ice was reorganized during the MPT. Yeah, thank you for your attention.
Thank you very much, Yamamoto-san. So I'd like to take questions. Should raise? Oh, yeah. Yeah.
I don't see Masa, but if you see me, I get a question.
Yeah, it's okay. Jiro, you can start.
Thanks, Masa.
Other people raise hand. Yeah.
That was a very interesting talk. You hear me?
Yes.
That was a very interesting talk. I get two questions. First, when you reconstruct from the lake box the CO2, you say there is a discrepancy with the blue ice, but what is the constraint on age of your blue ice concerning the age of the CO2 that you measure on the blue ice? This is my first question. And my other question.
Yeah, okay. Yeah, I want to answer the first question. Yeah, I'm not familiar with ice core, but they used the argon isotopes. Argon isotopes gradually changed from the beginning of the Earth to the present. Gradually, slowly isotopic ratio changed. So then they measured the argon isotopic ratio, then determine the age. So the error is quite large. I show the error bar. Yeah, this one. You see, this horizontal bar indicates the age errors.
Okay. No, I don't see, but I trust you. And my second question is that you show a very beautiful correlation between the C13 and the CO2, the C13 of the this is true for the last 800 kilo years. But when but when you do that, you base that correlation before the NPT. Maybe this correlation before the NPT is not the same.
Yeah,
so I was wondering how far this hypothesis was pivotal or not for your conclusion.
Yeah, it's a very good question. Yeah, and within the 800,000 years, we separated, the time interval, the early half and the later half. Then the correlation is very similar. This is statistically equal, actually. So, and also we moved the time window, from older to younger. Then we obtained the slope and the intercept of this, calibration. This is also stable. So this means the within 800,000 years, the calibration was stable. But this doesn't guarantee, the calibration is true before the 800,000 years ago. It's true, and I suppose that the this calibration is affected by precipitation and temperature. But the our proxy record indicates that the temperature range and precipitation range is almost the same as the during the last 800,000 years. So I think this encourages us, to apply our calibration obtained during the last 800,000 years to the older period. This is my answer. Yeah.
Okay, thank you.
Yeah.
I saw the hands, but it's disappeared.
Somebody raised a hand.
Yeah, but it's disappeared from my screen. You can start. Yeah, Litla, Kate.
Oh, Kate.
Kate, please.
Hello, Masanobu-san. Can you hear me?
Yeah, nice to see you.
Nice to see you again. Yes, this is a wonderful record. Thank you for sharing with us. I guess I have a similar question, sort of building on this applicability. How far back can we push this? Because we are trying to generate some very similar data from site 1445, so the sister site for 46, but over the Pliocene. So we're really interested in that late Pliocene, early Pleistocene transition, where we know, well, we think we know from the boron isotopes that there should be a drop in CO2. But the CO2 levels are probably higher there, more like, more than 400. So do you think maybe you could sort of use a similar calibration or piggyback on the 1446 calibration?
We also analyzed the 4045 actually during the last 800,000 years. The calibration was very similar to site 1446 actually. And so hopefully the calibration obtained, the recent 800,000 years can be applied to all the direction. Hopefully, but I want to say that maybe we have to get the information about the temperature and precipitation as well. Then if the temperature and precipitation range is the same as the late Pleistocene, then maybe to some extent we can have the confident of the CO2 record.
Yeah, I wonder if there's a sweet spot in the CO2 sensitivity. So if you go too high with your CO2, I wonder if your C3, C4 balance is less sensitive, but I guess we don't know that. The calibration is extrapolated, to the higher CO2 range. So within the recent 800,000 years, then the calibration equation is not a serious problem. But if we go to the high CO2 world, then calibration will be very, very serious, I want to say. So we need some constraint of CO2 actually. For instance, blue ice and also precise boron isotope data, etc. Yeah, we're working on the boron isotope. I'll let you know.
Yeah, definitely.
Thank you.
Yeah, thank you.
So thank you very much. I still see hands, but I would like to first start Axel's talk, and I will keep the Zoom open. So if you can stay, you can continue the discussion after the whole discussion time. So I would like to change to next speaker, Next speaker is Axel Timmermann from IBS Center for Climate Physics. And so, yeah, title is the Simulating 3 Million Years of Earth History with CGCM. Please, Axel.
Thank you very much, Masa. So this is work done mostly in collaboration with Kyung-Suk Yoon, who conducted the simulations as well as much of the analysis, Elke Zeller, Xiaoyang Ron from our center, then Pasquale Raya from the University of Naples, Matteo Villeit and Andrzej Ganopolski from PIC. And can you see my, oops, okay, can you see my screen?
Yes, I do.
Okay. The motivation for this study was actually, we are interested in understanding the evolution of our genus Homo and whether climate actually played a major role in some of the extinction events probably, but also some of the speciations that occurred in this rather complex tree of our ancestors. But it's very difficult to get proxy data from the sites where we have evidence for human presence. So we thought it would be very nice to have a comprehensive and long climate model simulation that covers the entire time period of our genus Homo. So what is the advantage of transient climate modeling? Quite easy. Well, we can compare the simulations directly with proxy data in time. We can understand leads and lags to forcings and other locations as well. We don't make any equilibrium assumptions necessarily. We can study internal variability such as El Nino, how that changes in response to these forcings. In a transient way, we can look for abrupt changes in the system, and we can also use these climate models actually to develop proxy age models. That's something that I have tried to convince the community many times. I think that these physical climate models for certain aspects provide a much more consistent way of building age models than statistical age models. Okay, what did we do? We used the Community Earth System Model 1.2.2. That's a full couple general circulation model, atmosphere and ocean. And we ran it to cover the entire history of the last 3 million years. And the resolution of the simulation is 3.7 degree. And we can run on our supercomputer Aleph about 300 years per day. And you can quickly figure out we would still be running for a long time in order to cover 3 million years. So in order to conduct such a long simulation, we have to actually chop up the simulation in different chunks, which we can run in parallel. I will describe that in the next slide. We generated about 500 terabytes of output, and some of the output, some of the key variables are available for all of you to analyze. So first, we needed to come up with a forcing, and of course, let's start with the greenhouse forcings. CO2, as we just heard, is a very interesting challenge because we only have rather scattered data, blue ice, boron data prior to the Epica ice core. And that, of course, changes now with Yamamoto-san's record. After that, of course, we have the Epica core CO2s, so that can be used quite easily. We calculated, in order to get the methane, we did a correlation between the benthic delta 18O and the methane, and the same for N2O. It's not the best we can do, I think, but both of these factors don't play such a major role. Then, in order to obtain CO2 reconstruction going back to 3 million years, we used the Climber transient climate model simulation that was conducted by Matteo Villeit and Andrzej Ganopolski in 2019. So they have an intermediate complexity Earth system model with full carbon cycle and full ice sheet coupled, and they were able to first reproduce quite nicely this first period, late Pleistocene, and by running it from 3 million years all the way to now, they also obtain a CO2 record covering this kind of mystery period. And so this is one of the key forcings that we use, and we can discuss this later on, in particular also in the context of Yamamoto-san's results. So, of course, the greenhouse gas forcing is obtained in the way that I just described. We also have the ice sheet forcing for the last 3 million years from the same intermediate complexity model simulation. Again, I have to emphasize our model does not have a fully interactive carbon cycle and ice sheet, so we use the data generated by a simpler climate model. And of course, the orbital forcing is relatively straightforward. In order to conduct these runs, we ran many different chunks actually in parallel. Otherwise, the computing time would just be too long. And there are then, we always start from an interglacial and run into the next interglacial and even a little bit further. So we have overlap between the different chunks, and then we can evaluate in these overlap periods whether there are any spin-up issues that we need to consider. The model simulation has been used for a wide variety of projects. So far, we are looking currently at monsoon systems and ENSO, the Antarctic ice sheets and Southern Ocean dynamics. A presentation paper of this simulation is currently in review in a Climate of the Past discussions. Elke Zeller published a paper where she used that 3 million year simulation in order to force biome 4. So we have a long-term reconstruction of vegetation. And human habitats were studied in a recent study in Nature last year. And we have 2 more studies coming out in Science. And I saw Vas and Zhao Yang are actually also listening in. And we have also a mammal model that simulates up to 2,000 mammal species, so we can also study their behavior back in time. Okay, so how reliable is this climate model? And this is just a glimpse of some of the paleo proxy comparisons that we can do. We'll see more later. This is for precipitation variables. This is for temperature sensitive proxies. And what we're seeing here is just a snapshot over the last 400,000 years. And overall, you can just glance at it. I won't go through all the details on this slide. But the precipitation variability, in particular the precessional cycle in the tropical regions, is nicely picked up by our model. And on the other hand, if we look at temperature records, we see much more the CO2/ice sheet driven 80 to 120,000 year variability. Okay, so let's go through that a little bit more in detail. The simulation covers also this mid-Pleistocene transition. And the main changes that you see actually in the orbital frequencies that occur in our climate model simulation, they're included in the ice sheet and in the CO2 forcing. So we are not solving the mid-Pleistocene puzzle here. This was already addressed in the original Willeit and Ganopolsky climate model simulation. The orbital forcings, we have, of course, very nice precession variability, which is the pacemaker for a lot of the tropical climate change, hydroclimate change, with timescales of 100,000 years and 400,000 years. We'll come back to the long eccentricity cycle later on. And we have the 1.3 million year amplitude modulation of the obliquity, which we can also see in some of the records later on and also in the climate model simulation. We will go through some of the records in more detail. Shown here is the Herbert tropical SST stack. So Timothy Herbert included several proxies, alkinone-based temperature reconstructions in one composite. And we can compare our model simulation with the tropical SST stack, and it matches quite nicely. In particular, we have also this gradual cooling, which I think is still CO2 induced, even though Yamamoto-san does not see much of a trend there in that time period. What we see is that our model simulation generates definitely more precessional variability in temperature and also CO2. And that's something we can discuss further. What is actually the main periodicity? Are we seeing much more the 41 kilo-year variability in the CO2, or is there a possibility even for higher frequency precessional variability? Anyways, we can go through some other records. You can see many of them show this gradual cooling trend that we are familiar with going from the late Pliocene into the Holocene. However, in some other records, such as in the Western North Pacific and South Pacific, SST records, we can capture this variability amplitude-wise quite nicely, also timing-wise. However, these records, interestingly, don't show any gradual cooling. They're pretty much flat. So that leaves some room for interpretation as well as discussion. We will go very quickly through some of these records. And this is supposed to be an overview talk. I won't be able to discuss all of these comparisons with you. The temperature in Antarctica, according to our model simulation, would have a very nice gradual cooling trend following that transition in CO2. And pretty much the temperature in Antarctica is CO2 driven in our model, as well as there are some heat flux changes. But as I mentioned earlier on, the forcing in Willeit and Ganopolsky has both an obliquity and a precessional cycle in the early Pleistocene. Okay, we can jump into some of the monsoon system comparisons. This is a nice record also by Steve Clements, where we can see some of the proxy variability, which is indicative of changes in the hydroclimate, really matches beautifully, even on these longer time scales, even on the 400,000 year time scale with our simulation in black. If we look at other records, some of the variability is captured quite nicely. Overall, if we do a side-by-side comparison, you would expect some mismatches, which could be due to the imperfection of the proxy data, but also of the climate model. But something to mention here, we have actually 400,000 year variability in the precipitation, not only in the amplitude modulation of the precessional cycle, but also in the mean. Okay, westerlies is an interesting one. There is big discussion whether westerlies play a role in driving atmospheric CO2 outgassing from the deep Southern Ocean. And there are several, proxy records that could respond to westerlies in the North Atlantic, South Pacific, and South Atlantic. And one of the interesting features is, well, basically all the way to 1 million years, these proxies quite nicely agree with our model simulation. Prior to that, it's getting pretty wild, but also the comparison between the proxies themselves is starting to lose consistency. So that's something we should keep in mind. We should not only look at one of the proxies sensitive to westerlies. But in any case, we can see that the westerlies in our model simulation clearly have a much stronger precessional variability. Some of that is also picked up in the higher latitudes in the proxy data. Then if we compare, for instance, the northern annular mode and the southern annular mode, both of them show this nice gradual weakening over time. And that is CO2 driven very clearly, because that's the only part in the forcing that really matters. But if we look again at the variability, both of them seem to have a very strong precessional cycle, in particular also the SAM. And that is relevant for also understanding CO2 changes, because the CO2 does, at least in the Epica time series, does not have much of a precessional variability, much more, of course, 80 to 120 and 40 kiloyears. So that's an interesting one, which challenges the importance maybe of westerly changes in driving CO2 variability as previously suggested. So that's interesting. Also, precessional cycle variability in westerlies is different from a paper that I wrote several years ago, where we used an intermediate complexity model, Love-Klim, which shows much stronger obliquity variable. So this is a much more complex climate model here, fully coupled atmosphere-ocean, and a coupled general circulation. So we see different responses. Okay, if we look at ENSO, this is, I should have mentioned, our model simulation is orbitally accelerated. So instead of the 3 million years of orbital history, which we still include, the model simulation itself is squeezed to 600,000 years. So it's called orbital acceleration. So in total, we are dealing with 7.2 million months. So you can imagine doing analysis with a time series, global time series that is 7.2 million months long is quite a challenge. And this is just the ENSO time series, and I don't want you to look at something specific. We will do that in the next one, but you can understand that this monthly analysis is actually quite a challenge for even our data analysis capabilities. But what we can do instead is we can look at the variability in the NINU3 area, so the Eastern Equatorial Pacific. This would be the EP El Nino, and we have the CP El Nino, which is showing the variability much more in the Central Pacific. and we can calculate the ratio, which tells us the flavors of El Nino, whether it's more in the east or in the west. And one thing that is quite clear, you see the precessional cycle is the dominant feature, but the precessional cycle itself is amplitude modulated by the 100,000 years as well as by the 400,000 years. So again, the 400,000 year dominant eccentricity forcing starts to creep into our data, in particular in the early Pleistocene. One thing to note also is that if we look at the Eastern Pacific SST mean state, there is no relationship here because that's very much driven by the CO2. So the mean state changes in the East are not the drivers for the variability or for the changes in flavors. We can go a little more into the details and run a wavelet spectrum of this long time series. And what you can see is, well, there is a semi-annual cycle, there is an annual cycle, which itself is amplitude modulated again by the precessional cycle. And here's the ENSO variability changing. And if we zoom in a little bit more, we can see there is a peculiar 90 or 110 degree phase relationship between the precessional cycle in ENSO and in the annual cycle. And that is very similar actually to the paper by Christina Karimperidou, who only looked at the Holocene, but the model is actually very similar, albeit a different resolution. AMOC, that people might be interested in this, has actually also precessional variability, but we should keep in mind that because we use this orbital acceleration of 5 and also this stitching technique, parallel chunks, there might be some disequilibrium effects here in our AMOC time series, but the surface variables are not affected by this. So I think we can reliably look at the variables in the atmosphere as well as the surface ocean. Sea ice, there is a very strong increase in the southern hemisphere. Sea ice also CO2 driven, and really a mode switch in the variability here around the mid-Pleistocene transition. The northern hemisphere sea ice does not seem to show this very strong intensification, partly because it is also spatially or geographically limited. In any case, we can see that sea ice response, of course, would provide a positive feedback also for glacial interglacial CO2. More sea ice and for glacial conditions decreases the acid gas exchange, weakens the exposure time, and also creates more brine, which can bring down also heavy water with DIC. All right, so if we look a little bit more into the heat and energy transport in the climate system, we can study the heat transport. This is the global heat transport, both atmosphere and ocean, from 3 million years ago to today. And this looks very complicated. So we have switches between precession, obliquity, ice sheets, and here it goes the other way around and so on. So it's a rather complicated structure. So if we want to make some sense out of it, we just do an EOF analysis. And the first mode that we get is obliquity mode, essentially. But also the CO2-driven gradual trend is included here. And the second mode is an interesting one. It first becomes like a precession eccentricity modulated mode. And then after the MPT, we have a more complicated dynamics, which turns out to be the product between eccentricity and precession, eccentricity, CO2, and precession. So it's a combination mode. All right, so in order to understand the patterns of these modes, we can reconstruct several other features. And the first mode, which I call obliquity mode, has the effect that for positive principal components, we're pumping in heat into the extratropics. You can see that quite clearly in the associated temperature pattern. And there is less ice, sea ice and ice sheet, and that heat convergence is actually transported to the equatorial region. So we have a cross-equatorial transport, mostly provided by actually the ocean, partly compensated by the atmosphere, but not fully. So this is creating convergence in the system. And it makes sense also, we have weaker westerlies associated with this mode in the northern hemisphere. So we have less heat transport in the atmosphere. Okay, if we look at the other mode, which is much more like an interhemispheric mode, we are pumping in heat into the southern hemisphere, and there is also less sea ice, and that heat gets, or anomalous heat gets released in the northern hemisphere. So we have a cross-equatorial heat transport, both from the atmosphere but mostly from the ocean. There are also stronger transient eddies according to this mode, which contribute actually to the increased atmospheric heat transport. So if we understand these two modes, we also can understand the interaction between heat pumping into the equatorial region and divergence, as well as the swapping of heat between the two hemispheres. And that tells us something about the overall energy, or if you like, the enthalpy cycle in the entire climate system, which helps us understand also feedbacks in the fully coupled system prior to the MPT and post the MPT, and they're quite different. And if you're interested in that, you can look at the climate of the past discussion paper. Okay, past to future. This simulation, we didn't stop only in the Holocene, but we used the same climate model configuration also to run some simulations into the future to 2100, just to get an idea how does the recent warming compare to the paleoclimate context. And we can see, at least according to the simulation, the highest ever simulated temperature in the late Pliocene was exceeded about the year 2010 in our model simulation. So we would already be higher currently, according to this run, than any previous global mean temperature. And of course, we are neglecting millennial scale variability here and centennial scale. But that gives you some context. We can also look at the simulated trends. The recent trends are, as we know, about 1 degree per 100 years for the different scenarios. It depends on whether you're cutting down CO2 or not. And this is at least an order of magnitude faster in the time derivative of temperature as compared to what we have in the previous in the last 100 years and into the future. So this is definitely showing the rate of change is completely out of the natural range, and we know that. Okay, I just wanted to show this little video to demonstrate how you access the data, and I will give you a QR plot code later on. So you can click on the simulation on our climate data web server, and if you want to do a time series, for instance, of precipitation, you can click on time. And I think if you're interested in this simple procedure, I think we used a time series somewhere in Papua New Guinea, no, actually somewhere in China. We're looking at precipitation here over the last 2 million years only. It takes a little while to put the marker to time, and then you go to update plot, and everybody can do that. So it's openly available. It takes a little while, and then you get the time series of precipitation near Sanbao Cave. That was the example here. And you can do this for sediment cores. You can do this for winds and many other variables. So I won't go through all the details here, but you get the gist of it. And my last slide is about our ongoing efforts here at the IBS Center for Climate Physics. We have now coupled the CESM 1.2 model to the Penn State ice sheet model in both hemispheres, in the Northern Hemisphere and Antarctica. And we are now able to do fully coupled simulations from 80,000 years ago to present day. The period, the MIS5 period, is tricky because there are lots of multiple equilibria sitting there, trajectory divergence, and you're essentially integrating lots of errors during that time period. So that's still a work in progress. In this simulation, we keep the bathymetry fixed at LGM conditions. That's something to keep in mind. But in any case, this is the fully coupled simulation of the ice sheet and climate system, and we're just looking at the ice sheet height here in both hemispheres. Now you're getting into the deglacial period, and you see that most of the ice is gone. That's a good thing. And also we keep, at least in the Holocene, in the late Holocene, some ice shelves for the Weddell Sea and the Ross Sea, which is not easy actually. Okay, so that gives you some idea where we are. And if you're interested in analyzing our data, you can make a photo or screenshot of this QR codes. This guides you to the web page where you can play either with OpenDub if you're familiar, or LAS, Live Access Server, with the data. OpenDub is good for MATLAB, Python, and all these tools. And this is for the 3 million year biome run, which I briefly mentioned, published recently. And if you want to explore what Homo erectus or heidelbergensis did about 500,000 years ago, you can also look at the QR code. We have netcf files for that as well. And with that, I would like to thank you for your attention.
Thank you very much for lots of information, Axel. I'd like to take some questions from audience. You can either raise, Kira, no, you are just,
Jill is
Jill, you can start.
Jill, you are muted.
Jill, you can start. Yeah.
This would be better to answer my question. I'm no more muted. Yes, actually, it was quite interesting. Well, personally, I would have preferred to hear about our gen Homo dispersal linked to that simulation. I would have much more questions. But due to the fact that you only talk about the dynamics, I have two main questions. The first one concerns the starting of your simulation. You start at 3 million years. And at 3 million years, I want to know if you account for the 20 meters of changes in sea level, and if you account about the paleogeography. This could be quite important, because if you look to the PMIP, depending on the sea waves, you can begin with a very small or strong hammock, and this could be important for your simulation.
So
this is
the
first thing.
Can I first answer your first question?
Yeah, sure.
So this is very, very difficult to change the bathymetry during the simulation. And for instance, imagine you started switch from an ocean point to a land point. What are you going to do with the salinity? What are you going to do with the currents? Or you have a land point and it becomes an ocean point. How do you actually generate this? So this is something very, very difficult. I think the only group so far I know that managed that in a transient way is the group at Max Planck. But we did not invest the time to change the bathymetry during this simulation following the ice sheet. So we keep the LGM bathymetry for the entire time period, and that's a very strong oversimplification. But given the fact that if you change during the run land sea mass and have to account for salinity changes, current changes, and so on and so forth in a pretty ad hoc way, I think that one will also have its difficulties. Yeah.
Okay, Axel, my point was not exactly that. I agree that only Uwe has succeeded to do that. But my point was not that. My point was that if you begins with a starting point during, for instance, Pliocene, depending on the paleogeography you will use, you will have an hammock which will be quite different. And this means that a dynamics which we use, and because you are not using any more anemic, you cannot make many simulations depending on the starting point. But we can discuss that. I don't want to talk too much. So my second question is
again,
that, of course,
the starting point, let me just say, we don't only have one starting point. As I mentioned, we have different chunks that we simulate. The starting point is the starting point in the, let's say, orbital in the boundary conditions. But the way we simulate is we have glacial interglacial chunks. And these ones later on, they will be stitched together. And otherwise, there is no other way of running 3 million years, even unless you use very high orbital acceleration. But yeah, we don't have the paleogeography of 3 million years as a starting point of our first chunk.
And my last question, very quick, to let the other people ask questions. You know that it's a very good work. It's the work of Matthias and Andre concerning the reconstruction of CO2. It's at least consistent with the model. But there is some weakness in this reconstruction when you compare it to data from 3 to 2 million of years. So did you check that also? Did you see what did you get if you take, for instance, a Martinez-Boppy reconstruction of CO2, just to check what is the influence, the impact of a different CO2 scenario before the MPT, for instance? I mean, between 3 and 1 million of years, when we don't have the bubbles.
Frankly, for me, the best CO2 proxy I have seen so far is the Herbert SST proxy. So these are different locations, alkaline temperature locations from the tropical oceans. They are not much affected by the orbital forcing directly. They are not much affected by the ice sheet themselves. And so the temperature in these areas, you can test it in other climate models, is very much driven by the CO2. So the Herbert record shows obliquity scale variability prior to the MPT compared to Willite, which has the much stronger precessional cycle. So I'm a bit concerned about the strong precessional forcing in the MPT CO2 reconstruction. We may be able to do another run later on with a better CO2, but that will, as you saw, 30 million or 40 million CPU hours is not trivial.
Okay. Thank you very much.
Thanks.
Thank you. Agatha Tibor, please.
Hi, yes, thanks for a nice talk. You're probably limited in what you can show now. I'm just wondering, have you analyzed, or are there studies underway that has looked at the location and strength of deep water formation and the age of the deep water and the variability of that and the drivers of that?
So there is nothing on the way, to put it this way. So you can look at deep water formation. If you know that we don't change the bathymetry, that may be not that dramatic, but in that area. But so as I mentioned, we have these orbital, these chunks in the simulation. So going from one interglacial into the next interglacial, and starting actually in that interglacial another run and doing this all in parallel, there could be mismatches actually in the deep ocean salinity, and we saw that. That may not directly affect your deep water formation sites, but it could affect some of the deep ocean circulation features. But if you're just interested in the atmospherically and maybe ocean related changes in buoyancy fluxes, the deep convection, you're welcome to look at these runs. So
what kind of ocean variables are saved?
We definitely have mixed layer depth saved. We have 3-dimensional temperature, salinity, UV. We have probably, and of course, a few others, but let's say the standard variables, and CSM has 2 mixed layer variables. I think we probably saved both of them. And so they are not on the data server. So if you took the QR code, they're not there, but you can get them by contacting us directly, because the real data set, 500 terabytes, is huge. We can't easily put it out there, but we're happy to generate the data for you if you're interested in it.
Thanks.
Okay, thank you. I'd like to officially close the PMIP wings, but as long as the speakers can stay, and if people want to discuss more, I will keep the Zoom open. So there is going to be a free discussion, but just because we promised 1 hour for speakers, just I officially close the session. We had as much as more than 60 people, which was very great, and thank you very much for 2 speakers, Yamamoto and Axel, and thank you for all the participants. And so it's going to be now the free discussion time, if the Axel and Yamamoto can stay. Yeah. So Mary, you can start if you like to.
Thanks. I had a quick question for Axel. Thank you very much. That was a really impressive talk, lots and lots of information. I was interested about the ENSO and the relationship with the mean state. So you kind of quoted that there was no relationship between ENSO variability and